Energy spreads evenly until no differences remain. The universe is a closed system. Energy cannot escape. It can only redistribute. Stars burn hydrogen, converting concentrated nuclear energy into diffuse radiation. That radiation spreads across space, cooling as it travels. Eventually, it becomes indistinguishable from the background temperature. Every process in the universe increases entropy. Stars fusing hydrogen, galaxies colliding, black holes swallowing matter. Even you reading these words, your body converts chemical energy from food into heat, which radiates into the environment. Entropy grows. The early universe had low entropy. Energy was concentrated in an incredibly hot, dense state. As expansion continued, that energy spread out. Particles cooled, atoms formed. Gravity collected matter into stars and galaxies, creating pockets of local order. But that order came at the cost of greater disorder elsewhere. The total entropy kept rising. Stars are entropy engines. They create order locally by fusing elements and powering planetary systems. But they radiate far more disorder into space through heat and light. The net entropy of the universe increases every second a star burns. Physicists calculate that the entropy of the universe has increased by roughly 10 to the power of 120 since the Big Bang. That number will continue growing. After stars die, black holes dominate entropy. A supermassive black hole contains more entropy than all the stars in a galaxy combined. When the black holes evaporate, they release that entropy as Hawking radiation. Eventually, all the energy in the universe will be spread so evenly that no temperature differences exist anywhere. No hot and cold, no energy gradients, nothing to drive any process. This is maximum entropy. At maximum entropy, the universe reaches equilibrium. Particles drift through space at uniform temperature, barely above absolute zero. Nothing interacts. Nothing changes. Time becomes meaningless because no processes mark its passage. This state persists forever. Entropy cannot decrease. The universe cannot spontaneously reorganize into stars and galaxies again. The arrow of time points in one direction only, toward greater disorder. Some physicists speculate about quantum fluctuations creating new universes, or spontaneous decreases in entropy over timescales, so vast they defy comprehension. After 10 to the power of 10 to the power of 10 to the power of 56 years, random fluctuations might create a structure resembling a universe. But these are mathematical curiosities, not practical escapes. For all meaningful purposes, entropy wins. The universe slides toward maximum disorder and minimum usable energy. Heat death is not just a possibility. It is a certainty written into the laws of physics. And the engine driving this decay is invisible. The greatest magic trick in physics is this: empty space weighs more than everything you can see. Take a cubic meter of empty space. Remove all matter, all radiation, every particle. What remains is not nothing. Quantum mechanics tells us the vacuum has energy. This vacuum energy is small, roughly 10 to the power of -9 joules per cubic meter. That seems negligible. Now consider the scale of the universe. The observable universe contains roughly 10 to the power of 80 cubic meters of space. Multiply that volume by the vacuum energy density, and you get a number larger than the mass energy of all visible matter combined. Dark energy, the force accelerating cosmic expansion, might be vacuum energy. If so, empty space itself pushes the universe apart. The more space exists, the more dark energy exists. Expansion creates more space, which creates more dark energy, which drives faster expansion. A runaway process with no endpoint. Scientists measuring the cosmic microwave background and distant supernovae calculated the energy budget of the universe. Roughly 70% is dark energy, 25% is dark matter. Only 5% is normal matter, everything we can see and touch. This seems impossible. How can empty space contain energy? Where does it come from? Quantum field theory provides an answer. Though the details are unsettling, the vacuum is filled with quantum fields. The electromagnetic field, the electron field, the quark field, dozens of others. These fields have ground states, minimum energy levels they cannot drop below. Those minimum energies are not zero. They contribute to vacuum energy. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum. Each particle contributes a tiny amount to the total energy. Add up every possible particle at every possible wavelength, and the calculation produces a catastrophic result. The vacuum energy should be 10 to the power of 120 times larger than what we observe. This is called the cosmological constant problem. Physics predicts vacuum energy should be enormous, so large that space would rip apart instantly. Yet measurements show it is almost zero, just barely large enough to drive the observed acceleration. Why is it so small? No one knows. Some physicists propose fine-tuning, that the constants of nature are precisely balanced to produce this value. Others suggest we live in a multiverse where most universes have different vacuum energies. We exist in one with a small value because only those universes allow matter and life to form. Neither explanation is satisfying. The first requires accepting an extraordinary coincidence with no mechanism behind it. The second requires believing in infinite, unobservable universes. What we do know is this: empty space dominates the universe. It outnumbers and outweighs normal matter by a vast margin, and it is winning the cosmic battle. Dark energy pushes galaxies apart, while gravity tries to hold them together. Dark energy grows stronger as space expands. Gravity weakens as matter spreads out. Eventually, dark energy will dominate completely. Every galaxy cluster will become an isolated island. Then every galaxy. Then every star system. Expansion will outpace all binding forces. The universe will be nothing but isolated particles in an ever-expanding void filled with dark energy. The void is not empty. It is full of the most powerful force in existence. And that force has a name we barely understand. Einstein called it his greatest blunder. Now, it might be the key to understanding why the universe is tearing itself apart. In 1915, Einstein developed general relativity, a theory describing gravity as the curvature of space-time. When he applied his equations to the universe, they predicted something unexpected. Space could not remain static. Gravity would either pull everything together into a collapse or allow everything to expand apart. Einstein believed the universe was static and eternal. To force his equations to allow a static universe, he added a term called the cosmological constant. This constant represented a repulsive force inherent to space itself, perfectly balanced against gravity to keep the universe from collapsing or expanding. Then, in 1929, Edwin Hubble discovered galaxies are moving apart. The universe is expanding. Einstein realized his cosmological constant was unnecessary. He reportedly called it his greatest blunder and removed it from his equations. 70 years later, astronomers discovered the expansion is accelerating. Something is pushing space apart, overpowering gravity. Einstein's blunder was correct after all. The cosmological constant represents dark energy. The constant describes energy density that remains uniform as space expands. Normal matter dilutes as the universe grows. Spread matter across more space and density drops. But the cosmological constant stays the same. Every cubic meter of space has the same energy density regardless of how much the universe expands. This property is bizarre. Where does the energy come from? If space creates more of itself and each new cubic meter contains vacuum energy, the total energy increases. Does this violate conservation of energy? General relativity says no, because the expanding space has negative gravitational potential energy that exactly balances the positive vacuum energy. The total remains zero. Measurements from multiple sources confirm the cosmological constant's value. Observations of distant supernovae, the cosmic microwave background, galaxy cluster distributions, and gravitational lensing all produce consistent results. The constant is roughly 10 to the power of -52 per square meter. That number seems arbitrary and specific. Why that value? A slightly larger constant would have prevented galaxies from forming. A smaller value would be undetectable. We exist in a universe with a cosmological constant perfectly tuned to allow structure formation early on while driving, accelerating expansion later. Some physicists propose that the constant changes over time. Maybe it was smaller in the early universe and has grown stronger. Maybe it will continue changing in the future. Current evidence suggests it remains constant, but we have only measured it over a few billion years. Cosmic timescales are much longer. If the cosmological constant is truly constant, the future is determined. Expansion accelerates forever. Galaxy clusters separate. The observable universe shrinks. Heat death arrives. The universe spreads into infinite cold darkness. If the constant changes, all predictions collapse. A strengthening constant could trigger the Big Rip, tearing apart atoms within billions of years. A weakening constant might slow expansion, possibly even reversing it into a big crunch. We would need new physics to predict which path we follow. For now, the cosmological constant stands as evidence that space itself is active. Empty space is not passive background. It participates in cosmic evolution, pushing against gravity, shaping the fate of everything. And that fate is rushing toward us faster than we ever imagined. Right now, at this exact moment, you are living in the golden age of the universe. Look up at the night sky. You can see stars, galaxies, nebulae. Billions of years from now, none of that will be visible. The universe is roughly 13.8 billion years old. Star formation began a few 100 million years after the Big Bang. Galaxies assembled over billions of years. Complex chemistry developed, planets formed, life emerged. This period of complexity and light represents less than 5% of the universe's total lifespan. The remaining 95% will be darkness. Current observations and models predict star formation will cease in approximately 1 trillion years. That gives us roughly 100 times the current age of the universe before the last stars die. It sounds like a long time. It is not. Compare 1 trillion years to the time after the last star dies. After stars cease forming, stellar remnants will persist for 10 trillion years, slowly cooling. Then black holes dominate for 10 to the power of 100 years as they evaporate. Then proton decay, if it occurs, takes 10 to the power of 40 years to erase matter. After that, the universe exists in a nearly eternal state of maximum entropy. Do the math. The age of stars represents 1 trillion years. The age of darkness represents 10 to the power of 100 years or longer. That is 10 to the power of 88 times longer. The ratio between them is incomprehensible. We exist in the first fraction of a percent of cosmic history. The brief moment when stars shine, when galaxies cluster, when chemistry creates complexity. The window during which life is possible. Think about what this means. You are alive during the only era when the universe is interesting. Before this era, the universe was too hot and uniform for structure. After this era, the universe will be too cold and empty for change. Right now, in this narrow slice of time, the cosmos is at its peak. Future beings, if any exist trillions of years from now, will envy us. They will live in a universe containing only a few dying stars and cold remnants. They will have no evidence of the Big Bang because the cosmic microwave background will have redshifted into invisibility. They will see no distant galaxies because expansion will have carried them beyond the event horizon. Their scientists will calculate and theorize, but they will lack the observational evidence we have today. They might conclude the universe is small, static, and empty. They will be wrong, but unable to prove it. We are the lucky ones. We can observe galaxy collisions, star formation, black hole mergers, gravitational waves from cosmic events. We can trace the history of the universe back to moments after the Big Bang. We can see the cosmic web spanning billions of light years. But this privilege comes with a burden. We know what is coming. We see the darkness approaching. Every measurement confirms that expansion is accelerating. The observable universe is shrinking. The void is winning. Our existence is a cosmic accident, a brief flicker of complexity in an ocean of entropy. We arose during the only era when consciousness could observe a rich, dynamic universe. Soon, cosmically speaking, that era ends. And when it ends, nothing we do can bring it back. You will never visit another galaxy. Neither will your descendants, no matter how advanced they become. The speed of light is an absolute barrier, and the universe is expanding faster than we can cross it. Light travels at 186,000 miles per second. Nothing can move faster. This is not a technological limitation. It is a fundamental law woven into the structure of space-time. Einstein's relativity proves that traveling at light speed requires infinite energy. Exceeding it is impossible. Andromeda, our nearest major galactic neighbor, sits 2.5 million light-years away. Even traveling at light speed, crossing that distance would take 2.5 million years. Our current fastest spacecraft moves at roughly 40,000 miles per hour. At that speed, the journey would take over 70 billion years. But wait, the universe is expanding. Andromeda is actually moving toward us, pulled by gravity. In roughly 4 billion years, the Milky Way and Andromeda will collide and merge. We might survive the collision, but eventually we become part of the same galaxy. Look beyond Andromeda. The Triangulum galaxy sits 3 million light-years away and is receding. The Virgo cluster, roughly 50 million light-years distant, is accelerating away faster than we could ever chase. Every galaxy beyond our local group is moving out of reach. Calculate the numbers. To reach a galaxy 50 million light-years away, you would need to travel at light speed for 50 million years. But during that journey, space expands. The galaxy moves farther away. By the time you arrive at where it was, it is now somewhere else. You can never catch up. Even generation ships, hypothetical spacecraft carrying thousands of people across multiple lifetimes, fail against cosmic expansion. Launch a ship toward a distant galaxy at 99% light speed. Thousands of generations live and die on board. When they finally arrive, they find the galaxy has moved billions of light-years farther due to expansion. They spent their entire civilization chasing something they could never reach. The cosmic event horizon marks the boundary beyond which escape is impossible. Galaxies beyond 16 billion light-years are receding faster than light. Even if you could travel at light speed, you could never reach them. The expanding space carries them away faster than you can cross it. This creates a prison. The local group is our cage. Gravity binds these 80 galaxies together, protecting them from cosmic expansion. Everything else is leaving. The bars of our prison are made of space-time itself, expanding in every direction, trapping us forever. Some physicists speculate about wormholes, shortcuts through space-time that could allow faster-than-light travel. Others discuss theoretical concepts like warp drives that bend space around a ship. None of these have been demonstrated. They might violate fundamental physics. Even if they exist, they require exotic matter and energy densities that might be impossible to create. For all practical purposes, we are stuck. The galaxy we live in, and the few dozen galaxies gravitationally bound to it, represent the entirety of the accessible universe. Everything else is forever out of reach. We are cosmically alone, not just because we see no aliens, but because the universe itself ensures we can never visit most of it, and most of it will remain a mystery. Roughly 95% of the universe is invisible. We can never observe it, never measure it, never know what exists there. The observable universe is defined by the distance light has traveled since the Big Bang. Currently, we can see roughly 46 billion light-years in every direction. This gives us a sphere containing approximately 2 trillion galaxies. That sounds comprehensive. It is not. The entire universe is vastly larger than the observable portion. How much larger? We do not know. It could be 1,000 times larger, 1,000,000 times. Infinite. We cannot measure beyond the edge of observation. Light from regions beyond 46 billion light-years has not had time to reach us yet. Some of that light will arrive eventually, expanding our view slightly, but most will never arrive because cosmic expansion carries those regions away faster than light can cross the gap. Current models suggest the universe is flat and likely infinite in extent. If true, the observable universe is an infinitesimally small bubble in an endless ocean. Imagine standing on a beach and scooping up one grain of sand. That grain represents what you can observe. The rest of the universe is every beach, every desert, every grain of sand on Earth and beyond. You will never see it. What exists in that unknowable region? Probably more galaxies, more stars, more planets. The same physics should apply everywhere, but we cannot confirm this. Maybe the laws of nature vary across cosmic distances. Maybe the cosmological constant is different elsewhere. Maybe structures exist that are impossible in our neighborhood. We will never know. Some physicists propose the universe might be curved in ways we cannot detect locally. If so, the shape of the universe beyond our observation could be anything. A torus, a hypersphere, something with no analog in human experience. The math allows these possibilities, but provides no way to test them. The cosmic event horizon complicates this further. Galaxies are crossing that horizon right now, disappearing from view forever. With each passing moment, more of the universe becomes inaccessible. The pool of knowable reality is shrinking. In 100 billion years, observers in our galaxy will see only the local group. Everything else will have vanished. Future scientists will have no evidence that 2 trillion other galaxies ever existed. The cosmos will appear small and local. They will be fundamentally wrong about the nature of reality, with no way to discover their error. This might already be our situation. Maybe the universe we observe is a tiny fraction of something far larger and stranger. Evidence from earlier epochs might have already redshifted beyond detection. We could be missing 99.9% of cosmic history and never know it. The unknowable universe mocks us. It exists, full of wonders we can never see, discoveries we can never make, questions we can never answer. The speed of light and cosmic expansion create an information barrier more absolute than any physical wall. We are trapped not just in space, but in knowledge. Most of reality is forever beyond our reach, and what we can observe reveals a terrifying truth. The void is not passive. It is aggressive, growing, consuming everything. You might think of empty space as nothing, an absence waiting to be filled. This is wrong. The void is an active participant in cosmic evolution. It expands, pushing matter apart. It contains energy, driving acceleration. It destroys structure, forcing the universe toward maximum entropy. Dark energy fills the void with a force that overpowers gravity across cosmic distances. Every second, this force grows stronger as space expands. More void means more dark energy. More dark energy means faster expansion. Faster expansion creates more void. The cycle feeds itself. This is not random drift. This is active destruction of cosmic architecture. The filaments connecting galaxy clusters are being stretched and torn. The walls surrounding voids are being pushed outward. The cosmic web, the largest structure in existence, is being systematically dismantled. Measurements show voids are growing faster than simulations predict. Something about the void itself accelerates expansion beyond what gravity alone would allow. The emptier a region becomes, the faster it expands. Empty space creates more empty space at an accelerating rate. Think about what this means for matter. Galaxies, stars, planets, atoms. All of it is temporary structure imposed on the void. The void tolerates this structure for now, held back by gravity in dense regions. But in the spaces between, the void is already winning. It expands freely, creating cosmic deserts, where nothing exists. Eventually, the void wins everywhere. Dark energy overpowers gravity across all scales. Galaxy clusters dissolve, galaxies shred apart, stars scatter into isolation. Planets drift alone through expanding darkness. Atoms exist as isolated particles, separated by distances growing every second. The final state is not a return to equilibrium. It is the triumph of the void, an eternally expanding emptiness with isolated particles drifting through it, growing more distant forever. The void does not fill with anything. It simply grows, creating more of itself, diluting what little matter exists to insignificance. Scientists debate what the void truly is. Is it quantum vacuum energy, a fundamental property of space-time, a field we have not yet identified? We observe its effects, but do not understand its nature. All we know is that it exists, it dominates, and it wants the universe empty. 70% of everything is this force. 70% of reality is dedicated to tearing apart the other 30%. The universe is not neutral. It is hostile to structure, to complexity, to life. We exist despite the universe, not because of it. The void has been winning since the beginning. Immediately after the Big Bang, the universe was dense and hot. Structure began forming. But the void was there, expanding space, diluting energy. For billions of years, gravity fought back, collecting matter into stars and galaxies. Now dark energy is taking control. Expansion is accelerating. The void is reclaiming everything. You exist in the brief interval when structure is possible. Before this, the universe was too uniform. After this, it will be too empty. Right now, in this narrow window, complexity emerged. Life developed. Consciousness arose. And that consciousness discovered it lives in a universe being actively destroyed by the void. The emptiness is not waiting in the future. It is here, surrounding you, expanding every moment. It fills most of the space you can see. It dominates the universe completely. And it is terrifying because it is winning. Something impossible is happening in the largest voids. They are becoming colder than they should be. The cosmic microwave background is the afterglow of the Big Bang, radiation that fills all of space at a temperature of roughly 2.7 degrees above absolute zero. This is the baseline temperature of the universe. Nothing should be colder unless actively cooled. Yet measurements from the Atacama Cosmology Telescope reveal that the largest cosmic voids have temperatures slightly below this baseline. The difference is tiny, roughly 10 millionths of a degree, but it exists, and it should not. These cold spots appear in regions where supervoids stretch across hundreds of millions of light years. When cosmic microwave background radiation travels through these voids, it loses energy. Photons climbing out of the gravitational well created by surrounding matter use up energy, cooling slightly. This is called the integrated Sachs-Wolf effect, and it is confirmed science. But here is the disturbing part. The cooling is stronger than models predict. Voids are expanding so fast that radiation passing through them experiences more energy loss than calculations suggest. Dark energy is inflating these regions faster than standard cosmology allows. Think about what this means. The largest empty regions in space are not just voids. They are cold traps, areas where even background radiation cannot maintain normal temperature. These regions are becoming isolated from the rest of the universe, not just spatially, but thermodynamically. Some physicists studying the data noticed something stranger. The cold spots are getting colder over time. Observations from 10 years ago showed weaker cooling than current measurements. The voids are actively draining energy from radiation passing through them at an increasing rate. This suggests the voids are not passive. They are growing more extreme, more empty, more isolated. As dark energy strengthens and expansion accelerates, these regions become cosmic wastelands where even the faint warmth of the Big Bang cannot persist. If you could somehow exist inside one of these supervoids, you would experience the coldest natural environment possible, colder than intergalactic space, colder than the emptiest regions between galaxy clusters. You would be in a bubble of space cut off from the rest of reality, cooling toward absolute zero faster than anywhere else. The coldest void discovered so far is the Eridanus supervoid, a region roughly 1 billion light-years across. The cold spot it creates in the cosmic microwave background is so pronounced that scientists initially thought the measurements were wrong. Multiple telescopes confirmed it. The void is real, and it is colder than the surrounding universe. As time passes, these cold voids will grow larger and colder. Eventually, they will dominate the universe. The warm, energy-rich regions where galaxies cluster will shrink to isolated islands in an ocean of cosmic cold. You live in one of those warm regions now, protected by the presence of nearby galaxies. But the cold is coming. It expands at the speed of light, claiming more space every second. And the cold brings something worse than emptiness. Life exists because the universe had the right conditions at the right time. Those conditions are disappearing. When the universe was young, everything was hot and dense. Too hot for atoms to form, too chaotic for chemistry. Life was impossible. As expansion continued and temperatures dropped, a window opened. Stars formed. Heavy elements were created. Planets assembled. Chemistry became complex enough for biology. That window is closing. The universe is currently in its most life-friendly era. Stars burn steadily. Planets orbit in habitable zones. Organic molecules form in interstellar clouds. Water exists as liquid on billions of worlds. This golden age will not last. Star formation is declining. The rate at which new stars ignite has dropped by roughly 95% since the peak 11 billion years ago. Galaxies are running out of the cold gas needed to form stars. Collisions between galaxies, which trigger bursts of star formation, are becoming rarer as cosmic expansion spreads everything apart. In 1 trillion years, no new stars will form anywhere. The universe will contain only the stars that already exist, slowly dying one by one. Without new stars, no new planetary systems form, no new chances for life to emerge. But the problem starts much sooner. In roughly 5 billion years, our own star will exhaust its hydrogen fuel and expand into a red giant. Earth will be incinerated. Any civilization still dependent on this planet must leave or die. Where would we go? Other stars in our galaxy will still burn for billions of years, but most of those stars are red dwarfs, dim and unstable, prone to massive flares that strip away planetary atmospheres. The stable, yellow stars like ours are rare and getting rarer as they age and die. Cosmic expansion makes everything worse. As galaxies accelerate apart, the pool of accessible stars shrinks. Future civilizations will be trapped in their home galaxy, unable to reach the resources of neighboring systems. When their star dies, they have nowhere to go. The universe is also becoming more dangerous. As large stars explode as supernovae, they enrich space with heavy elements but also flood regions with radiation. Gamma-ray bursts, the most energetic explosions in the universe, occur regularly. Any planet in the beam gets sterilized. Over time, these catastrophic events will have swept through most of the galaxy. Fewer safe regions will exist, where life can develop without being destroyed by cosmic violence. Dark energy accelerates the isolation. Galaxy clusters separate. The local group becomes an island. Future beings will look at a universe containing fewer stars, fewer galaxies, fewer chances for life than we see today. The conditions that allowed your existence required 13 billion years of cosmic evolution. Stars had to form, explode, and scatter heavy elements. Planets had to assemble. Chemistry had to organize into biology. This process was lucky, rare, and utterly dependent on the universe being at the right temperature and density. Those conditions are fading. The universe is cooling. Matter is spreading too thin. Energy is diluting. The window during which life can exist is temporary, measured against cosmic time. We arose near the peak of that window, billions of years from now, consciousness will struggle to find footholds in a colder, darker, emptier cosmos. Trillions of years from now, life will be impossible. You exist during the brief era when the universe allows it. Before long, cosmically speaking, it will not. And the moment when we could have met others has already passed. If intelligent aliens ever existed nearby, we are too late to meet them. The galaxy is roughly 13 billion years old. Stars have been forming for over 12 billion years. If civilizations arose elsewhere, some would have appeared billions of years before us. They would have had enormous head starts. Where are they? The silence suggests either they never existed or they did exist and we missed them. Consider the timescales involved. A civilization lasting 1 million years is extraordinarily long-lived by human standards. But cosmically, 1 million years is nothing. It is a brief flash. If a civilization rose, spread across multiple star systems, then collapsed, we might never know they existed. Their radio signals would have crossed the galaxy and dissipated. Their megastructures would have decayed. Their artifacts would have been destroyed by cosmic erosion, asteroid impacts, stellar radiation. After 10 million years, almost nothing would remain. After 100 million years, even ruins on airless worlds would be ground to dust. The galaxy recycles everything. Stars explode, planets collide, black holes consume. Any trace of ancient civilizations gets erased over geological timescales. We could be surrounded by the remnants of dead cultures and never recognize them. But the deeper problem is expansion. If civilizations existed in other galaxies, the chance to contact them is vanishing. Galaxies beyond our local group are accelerating away. Their light still reaches us, but significantly redshifted. Radio signals from those distances would be stretched and weakened beyond detection. Calculate the window for contact. A galaxy 10 billion light-years away is receding at roughly 90% light speed. Any signal they send takes 10 billion years to arrive. By the time it gets here, their civilization might be extinct. Our response would take another 10 billion years. No conversation is possible across such distances and timescales. And that assumes they existed 10 billion years ago. If they arose more recently, their signals have not reached us yet. If they arise in the future, cosmic expansion will prevent their signals from ever arriving. The window overlaps only if civilizations exist simultaneously and close enough for light to bridge the gap before expansion tears it apart. The math is brutal. Civilizations must emerge within a few billion light-years of each other and within a few billion years of each other. Otherwise, the expanding universe separates them permanently. We arose 13 billion years after the Big Bang. Early in cosmic history, the universe was too hot and chaotic for complex chemistry. Stars needed to explode several times to create enough heavy elements for planets. This process took billions of years. If we are among the first intelligent species, the era of contact has not begun yet. We are early. But if civilizations arose 5 or 10 billion years ago, we are late. We missed them. Some researchers analyzed the Drake equation and included a time factor. They calculated that even if intelligent life is common, the temporal overlap between civilizations might be incredibly rare. Two species could inhabit the same galaxy but exist millions of years apart, never aware of each other. The Fermi paradox becomes even darker with this realization. The silence might not mean civilizations never existed. It might mean they existed and died before we could meet them. We are listening to a galaxy filled with ghosts. The window for contact is closing. Every second, galaxies recede farther. Every year, signals weaken. Every million years, potential civilizations rise and fall without ever connecting. We might be perpetually alone, not because we are unique, but because the universe expands too fast for anyone to meet. And beyond what we can see, something massive is pulling. Galaxy clusters are moving in the same direction, pulled by something we cannot see. In 2008, astronomers studying the motion of galaxy clusters discovered an anomaly. Hundreds of clusters, spanning billions of light years, were flowing in the same direction at roughly 400 miles per second. This motion was separate from cosmic expansion, an additional velocity pointing toward a specific region of space. They called it dark flow, and it should not exist. According to standard cosmology, the universe should be roughly uniform in all directions on large scales. No massive structures should exist outside the observable universe capable of pulling galaxy clusters toward them. Yet the data showed exactly that. Something beyond our cosmic horizon is exerting gravitational influence. The effect was detected by analyzing the cosmic microwave background radiation. When galaxy clusters move, they create tiny distortions in this radiation through the kinetic Sunyaev-Zeldovich effect. By mapping thousands of clusters, researchers found a coherent motion, all moving toward the same point in the constellation Centaurus. What could cause this? The leading theory is terrifying. Beyond the edge of the observable universe, something massive exists. A structure so enormous that its gravity reaches across the cosmic horizon, pulling matter toward it. This could be a supercluster, a collection of galaxy clusters thousands of times larger than anything we can see. Or it could be something else entirely. Some physicists speculate about massive structures from earlier cosmic epochs, density variations left over from inflation. Others propose more exotic ideas, collisions with other universes, remnants of a previous cosmic cycle, even evidence of a multiverse. The data has been controversial. Some studies confirm dark flow, others find no evidence for it. The effect is subtle, pushing the limits of current detection methods. Improvements in mapping the cosmic microwave background might settle the debate. But if dark flow is real, the implications are staggering. The observable universe is not isolated. It is influenced by structures we can never see. Gravity reaches across the cosmic horizon, connecting regions of space that can never exchange light or information. Think about what this means for our understanding of reality. We assume the observable universe represents a fair sample of what exists. If structures beyond the horizon are fundamentally different, larger, or stranger than what we see, all our cosmological models are incomplete. You could be living in an atypical region of the cosmos. The laws of physics might be the same everywhere, but the distribution of matter might not be. Other regions could contain structures dwarfing anything we observe. Supervoids larger than our observable universe. Megaclusters containing trillions of galaxies. We would never know. The cosmic horizon is an absolute barrier. Light from those regions cannot reach us. Expansion carries them away faster than signals can travel. Whatever exists beyond remains forever hidden. Dark flow suggests we are not alone in the universe, but connected to something vast and unreachable. Something pulling on us from beyond the edge of reality. And if structures that large exist, what else might be out there? You might not live in the only universe. You might live in one of countless universes, and yours is running out of time faster than most. The multiverse theory proposes that our universe is one bubble in an eternal, infinite foam. Cosmic inflation, the rapid expansion moments after the Big Bang, creates new universes constantly. Each bubble has its own physical constants, its own laws of nature, its own fate. This is not science fiction. Leading physicists including Alan Guth, Andrei Linde, and Alexander Vilenkin have developed mathematical models showing how inflation naturally produces multiple universes. The theory solves several problems in cosmology and makes testable predictions. But here is the disturbing part. If the multiverse exists, we are likely in a universe with an unusually large cosmological constant. Our dark energy is strong enough to drive accelerating expansion, but weak enough to allow galaxies to form. This balance is incredibly rare. Most universes in the multiverse would have either zero dark energy or catastrophically large dark energy. Universes with zero dark energy would eventually collapse in a big crunch. Universes with huge dark energy would rip apart instantly. Only a narrow range allows stable matter and life. We appear to exist in that narrow range, but the range is not stable. Our cosmological constant sits at a value where expansion accelerates but does not immediately destroy structure. Over time, this acceleration will tear everything apart. We are in a universe on the edge of instability. Other universes might be more stable. Universes with slightly less dark energy would expand forever without accelerating. Galaxies would remain visible indefinitely. The cosmos would cool slowly toward heat death over timescales even longer than our own. But we do not live in those universes. We live in one where dark energy dominates and expansion accelerates. Why? The anthropic principle offers one answer. We observe this universe because only universes like ours allow observers to exist. Universes with too much dark energy never form stars. Universes with too little dark energy might collapse before life evolves. We see what we see because we could not exist anywhere else. This seems unsatisfying, but it might be true. If trillions of universes exist with random values of physical constants, most contain no life. We necessarily find ourselves in one of the rare exceptions, and among those exceptions, we might be in one of the least stable. Some multiverse models suggest our universe is temporary. The false vacuum could decay, destroying this universe and potentially spawning new ones. The Big Rip could tear apart space-time itself, ending this cosmic bubble. Other universes would continue existing, unaffected. You could be living in a dying universe while countless others thrive. Universes where expansion does not accelerate. Universes where stars burn for quadrillions of years instead of trillions. Universes where intelligent life has billions of times longer to develop and explore. But you will never see those universes. The cosmic horizon of your universe is absolute. Other universes are not just far away. They exist in separate spacetimes, unreachable by any means. No signal crosses between them. No travel is possible. The multiverse makes our situation more tragic. Not only is our universe dying, but it might be dying faster than most. We are trapped in an accelerating catastrophe, while better universes exist forever beyond our reach. And within this dying universe, a strange possibility emerges. What happens to consciousness in a universe approaching heat death? One interpretation of quantum mechanics suggests you might never experience the end. Quantum immortality is a thought experiment derived from the many worlds interpretation of quantum mechanics. Every quantum event splits reality into multiple branches. You exist in all branches where you survive. From your subjective experience, you always find yourself in a branch where you continue existing. Apply this to cosmic timescales. As the universe approaches heat death, energy becomes scarce, stars die, planets freeze. Eventually, organized matter breaks down. In most branches of reality, consciousness ceases, but quantum mechanics allows for rare fluctuations. Even in a cold, dead universe, quantum fluctuations can spontaneously create organized structures. The probability is extraordinarily low, but across infinite time, low probability events become certainties. A random fluctuation could create a brain with memories, thoughts, awareness. A Boltzmann brain, appearing briefly in the void before dissolving. If consciousness requires organized matter, and organized matter can arise from quantum fluctuations, then consciousness never truly ends from a subjective perspective. You always find yourself in the branch where a fluctuation just created you. The universe could be dead for 10 to the power of 100 years. Then a fluctuation births a conscious mind. From that mind's perspective, no time has passed. This seems absurd, yet it follows from the mathematics of quantum mechanics combined with infinite time. The many worlds interpretation suggests all possible quantum outcomes occur. If even one branch contains consciousness, you experience it. But here is the truly disturbing implication. You are more likely to be a Boltzmann brain than a real person. The probability of a universe evolving stars, planets, and biological life is incredibly low. The probability of a random quantum fluctuation creating a brain with false memories of such a universe is higher. Not high, but higher. Given infinite time in an empty universe, fluctuations will create trillions of brief, isolated conscious moments for every actual evolved consciousness. If you accept this logic, you should conclude you are probably a Boltzmann brain. Your memories are false. Your surroundings are illusion. You are a brief fluctuation in an otherwise dead cosmos, moments away from dissolving back into chaos. Most physicists reject this conclusion, which suggests something is wrong with the reasoning, but identifying the flaw is difficult. The mathematics seems sound. The logic follows from accepted principles, yet the conclusion is unacceptable. Some theorists propose that consciousness requires not just organized matter, but continuous causal history. A Boltzmann brain has no past, only a momentary present. Without causal continuity, it might not be truly conscious. This would solve the paradox but requires assumptions about consciousness we cannot verify. Others suggest the multiverse eliminates Boltzmann brains. If new universes are constantly being created through inflation, young, energy-rich universes vastly outnumber old, dead ones. Real consciousness in young universes is more common than Boltzmann brains in heat death. The debate remains unresolved, but it highlights a deep problem. If the universe truly reaches heat death and persists in that state forever, quantum mechanics predicts strange possibilities for consciousness. Either awareness ends completely, or it becomes fragmented, appearing in brief fluctuations across eternity. Neither option is comforting, and both assume information survives. Nothing you do will matter. Every thought, every creation, every moment of your existence will be erased so completely that the universe will contain no record it ever happened. Information, in physics, refers to any distinguishable configuration of matter or energy. Your body contains information encoded in atomic arrangements. Your thoughts are information in neural patterns. Human civilization is information in buildings, books, and digital storage. All of it will vanish. The first law of thermodynamics states energy is conserved. The second law states entropy increases. But what about information? For decades, physicists debated whether information is preserved or destroyed. Black holes complicated this question. When matter falls into a black hole, it seems to disappear. The black hole grows slightly more massive, but the specific information about what fell in appears lost. An atom of hydrogen and an atom of helium produce identical black holes if they have the same mass. The information distinguishing them is gone. Stephen Hawking proved black holes evaporate through quantum radiation. As they shrink, they emit random thermal radiation containing no information about what fell in. When the black hole finally evaporates completely, the information is destroyed. This violated quantum mechanics, which requires information conservation. The resulting black hole information paradox has consumed theoretical physics for 50 years. Recent proposals suggest information might be preserved in subtle correlations in Hawking radiation, but this remains unproven. The paradox might not be resolved, but here is the larger truth. Even if information survives black holes, it does not survive heat death. As the universe expands and cools, information spreads across ever larger volumes. Particles drift apart at accelerating rates. Eventually, each particle sits alone in its own causally disconnected region of space. No interaction is possible. No information can be exchanged or retrieved. At that point, information still exists, in principle, encoded in particle states. But it is irretrievable, scattered across infinite distances with no possibility of collection or processing. Functionally, it is destroyed. Quantum mechanics allows information to be scrambled, spread across entangled states, encoded in ways that make retrieval exponentially difficult. After enough time and expansion, reconstruction becomes thermodynamically impossible. The energy required to gather and decode the information exceeds the total energy available. Think about what this means for you. Every memory, every experience, every relationship is information encoded in your brain. When you die, that information begins to decay. Your body decomposes. Atoms scatter. Within centuries, no organized trace remains. Human civilization might last thousands or millions of years, preserving some information, but eventually, Earth will be consumed when the sun expands. Our solar system will be scattered when the Milky Way collides with Andromeda. Any records we create will be destroyed. Even if we spread across the galaxy and preserve information for billions of years, expansion ensures it cannot last forever. Star systems separate, galaxies drift apart, information fragments across cosmic distances until it becomes irretrievable. The universe is an information shredder operating on the longest possible timescale. Everything you create, everything you preserve, everything you think matters will be ground down to random noise and scattered across an expanding void. The second law of thermodynamics is merciless. Order becomes disorder. Information becomes entropy. The arrow of time points toward erasure, and nothing can reverse it. Your existence will leave no permanent mark on reality. The universe will forget you completely, and the forgetting is already beginning. Space is not expanding at the same rate in all directions. Something is wrong with cosmic isotropy. For decades, cosmology assumed the universe is homogeneous and isotropic on large scales. Homogeneous means matter is distributed roughly evenly. Isotropic means space looks the same in every direction. These assumptions underpin the standard model of cosmology. Recent measurements suggest the assumptions might be wrong. In 2019, astronomers compared expansion rates using different methods. Type Ia supernovae in nearby galaxies showed one value. Measurements from the cosmic microwave background showed a different value. The discrepancy is small, roughly 9%, but it persists across multiple independent studies. This is called the Hubble tension, and it might indicate that expansion is not uniform. Space could be stretching faster in some directions than others. If true, the universe is not isotropic. It has structure on scales larger than we thought possible. Some researchers analyzed quasar data and found hints of directional dependence. Expansion appears slightly faster in one hemisphere of the sky than the opposite hemisphere. The effect is subtle, but statistically significant. Other studies found contradictory results. The jury is still out. But consider the implications if expansion is anisotropic. Our cosmological models assume uniformity. If the universe is structured on supercosmic scales, those models are wrong. The age of the universe could be different than we calculated. The fate of the universe could be different. An anisotropic expansion could mean we live in a universe rotating on scales larger than observable. It could indicate we are inside a giant cosmic bubble, a region where expansion differs from the universe beyond. It could be evidence of collisions with other universes, leaving directional imprints. Some physicists propose that dark energy itself might not be uniform. Maybe the cosmological constant varies across space. Regions with stronger dark energy expand faster. Regions with weaker dark energy expand slower. This would create an anisotropic expansion pattern. If dark energy varies spatially, the future becomes unpredictable. Our galaxy cluster might be in a region where dark energy is relatively weak, buying us extra billions of years before isolation. Or we might be in a strong region, facing faster expansion than expected. The Hubble tension could also indicate entirely new physics. Maybe our understanding of cosmic expansion is fundamentally flawed. Maybe additional forces operate on cosmic scales that we have not discovered. Maybe the universe is more complex than any current model suggests. Measurements continue. New telescopes are being built specifically to resolve the Hubble tension. Within the next decade, we might know whether expansion is truly uniform or whether the universe has directional structure we never suspected. If expansion is not uniform, it adds another layer of uncertainty to an already terrifying picture. Not only is the universe expanding and accelerating, but it might be doing so unpredictably, differently in different regions. You could be living in a cosmic neighborhood where the rules differ from everywhere else. Your fate might not match the fate of distant galaxies. The isolation might come faster than calculated, or slower, or in patterns we cannot predict. The universe refuses to be simple. Every answer reveals new questions, and in the far future, those questions lead to a disturbing possibility. In the distant future, false minds will vastly outnumber real ones. You might already be one of them. As the universe approaches heat death, thermal energy drops toward absolute zero. Stars die. Black holes evaporate. Eventually, space contains only isolated particles drifting through expanding darkness. Nothing happens. Nothing changes. But quantum mechanics never sleeps. Even in the coldest, emptiest regions, quantum fluctuations occur. Particles pop into existence briefly and vanish. Most fluctuations are simple, just a few particles. But given infinite time, larger fluctuations become inevitable. Eventually, a fluctuation will randomly assemble atoms into a complex structure. The probability is unimaginably low, but infinity is long. After 10 to the power of 10 to the power of 50 years, fluctuations will occasionally create organized matter. Some fluctuations will create brains, complete with memories, thoughts, and consciousness. These Boltzmann brains appear fully formed, exist briefly, then dissolve back into chaos. From the brain's perspective, it experiences consciousness. It seems to have a past. It might even believe it lives on a planet orbiting a star. All of it is illusion. The brain has no past. The memories are false, created by random atomic arrangement. The surroundings are not real. The brain exists alone in an empty, cold universe, a brief spark of organization before returning to disorder. Here is the mathematical horror. Given infinite time, quantum fluctuations will create vastly more Boltzmann brains than biological brains. Real brains evolved through billions of years of chemistry and natural selection. Boltzmann brains appear through random chance. Evolution is rare. Random fluctuations are inevitable given enough time. Calculate the numbers. The universe might produce trillions of evolved conscious beings across its first trillion years. But across the next 10 to the power of 100 years of heat death, random fluctuations will create 10 to the power of 10 to the power of 100 Boltzmann brains. The ratio is staggering. For every real consciousness, countless trillions of false consciousnesses will appear in the dead universe. If you are selected randomly from all conscious experiences that ever occur, you are almost certainly a Boltzmann brain. This conclusion follows from accepted physics, yet it seems absurd. You have continuous memories. You experience causal relationships. You observe a consistent external world. None of this matches the expected experience of a Boltzmann brain. But a Boltzmann brain could have false memories of exactly those experiences. The fluctuation that created it could include neural patterns encoding fake memories of a consistent past. The brain might exist for only seconds, experiencing what feels like a lifetime before dissolving. Most physicists reject this conclusion, which means something is wrong with the reasoning. Perhaps consciousness requires continuous causal history that fluctuations cannot provide. Perhaps the multiverse creates new universes fast enough that young, energy-rich universes always outnumber old, dead ones. Perhaps quantum mechanics itself changes in ways we do not understand, but no consensus solution exists. The Boltzmann brain problem remains one of the deepest paradoxes in cosmology. It suggests our understanding of probability, consciousness, or cosmology is fundamentally flawed. If you accept the standard models, you face an uncomfortable choice. Either reject consciousness as you experience it and accept you are probably a Boltzmann brain, or reject the models and admit we do not understand the universe as well as we think. Neither option is comforting. Both suggest reality is stranger and more disturbing than it appears. And as the universe continues expanding, one final truth becomes undeniable. Everything you can observe is about to disappear, not in billions of years, not in trillions. The isolation is happening now. Right now, at this exact moment, galaxies are crossing the cosmic event horizon and vanishing from view. Light that has been traveling toward us for billions of years is being swallowed by expansion. Stars are being erased from the observable universe as their light redshifts into undetectability. Current measurements show roughly 60,000 galaxies cross the event horizon every year. That number is increasing as expansion accelerates. By next year, more galaxies will be lost. The year after that, even more. The process is invisible to you. You cannot see galaxies winking out because the light from those galaxies has not reached us yet. When we observe a distant galaxy, we see its past. By the time its light arrives, the galaxy might already be gone, carried beyond reach by expansion. Think about this carefully. Some of the galaxies you see in deep space images no longer exist in the observable universe. They are still out there, still real, but their current state is forever hidden from us. The space between us has expanded so much that their light can never cross it. The Hubble Space Telescope and James Webb Space Telescope capture images of galaxies as they appeared billions of years ago. Those galaxies have aged. They have changed. Some might have been destroyed in collisions. Others might have spawned new stars. We will never know. The updated information cannot reach us. Expansion is accelerating. The rate at which galaxies cross the horizon is increasing. In 1 billion years, significantly more of the universe will be invisible. In 10 billion years, most of what we can currently observe will be gone. Scientists estimate that within 150 billion years, every galaxy outside our local group will have crossed the event horizon. The night sky will contain only the merged remnant of the Milky Way and Andromeda, plus a few dozen dwarf galaxies. Everything else will be invisible. But the isolation begins much sooner for practical purposes. In roughly 5 billion years, the sun will die. If humanity survives, we will be forced to leave Earth. We will look for new homes among the stars. But by then, thousands more galaxies will have vanished. The pool of potential destinations shrinks every moment. The universe you observe today is larger and more populated than the universe your descendants will see. They will inherit a smaller cosmos, and their descendants will inherit an even smaller one. Generation by generation, the visible universe contracts. This is not a distant problem. This is happening in your lifetime. During the decades you live, millions of galaxies will cross the event horizon. You are witnessing the early stages of cosmic isolation. The process is gentle now, barely noticeable, but it is relentless. Every second, space expands by roughly 46 miles for every 3 million light-years of distance. Multiply that by the age of the universe, and you see why distant galaxies recede so fast. The farther away something is, the faster it runs away. You exist in the final era when the universe is observable, not the final trillion years. The final era. Within cosmic time, this era is brief. Stars have shined for 13 billion years. They will shine for another trillion. But the era when we can observe most of the universe is already ending. The emptiness is not approaching. It is here.